Thank you for tuning in today. Hello, I'm Marissa Yates, a researcher working for the CEREMA in the Saint Venant Hydraulics Laboratory. And today I'll be presenting our work on equilibrium modeling of current and future beach evolution at Vougot Beach in France. Work that's being done with our thesis student Teddy Chatenier, as well as my colleagues Nicolas Lenantec, Serge Chouanès, and France Floch at the UBO. And a couple of master's students that have worked with us over the last couple of years, Gavin Bouvard, Matt Leary, Corentin Péton, and Nicolas Caillé. So today I'll be starting by giving some background and motivation before discussing beach morphological evolution models that are used for looking at predicting long-term, medium to long-term changes. I'll give you a brief description of our study site before presenting some of the results and summarizing at the end. Why are we interested in studying beach changes? As most of you who are present know, we're quite interested in evaluating coastal risks, in particular erosion and inundation. As shown in the bottom plot, figures here over a 3.5-year time period at Vougot Beach in Brittany, France, we see the evolution of the beach from 2013 to 2016, where the pictures are taken in nearly the same location, and we see the staircase going down to the beach, where in 2013, we see that there was a well-developed dune that was built around the staircase. And then a year later, in 2014, after the passage of a series of large storms, like the image shown in the top right, we have large waves that come and attack the bottom of the dune base. There's a significant amount of erosion, but then we see in 2016, 2.5 years later, how the beach has recovered. So we'd like to understand better the processes controlling this, and also to be able to predict them with models and allow us to help develop coastal management programs. So our objectives are to be able to look at predicting medium to long-term beach evolution at spatial scales that range from that of a beach to a region. And the challenge at these kind of scales is to have both accurate and efficient modeling of beach evolution, including estimates of the uncertainties we make when using these kind of models to predict the future changes. In the current presentation, we'll be looking at evaluating existing methods that are for predicting future changes, in particular taking into account the impacts of climate change. So talk about the different time scales of beach changes that go from very short time scales, from hourly to daily, that are caused by wave sequences and storms, through medium time scales that are on the order of seasonal to annual, that are forced by seasonal wave variability and wave climate changes, to long time scales. We're talking about decadal to centennial time scales. We're looking at wave climate evolution and changes, for example, in sea level. A variety of different families of models can be used to simulate these or predict beach changes at these different time scales, from process-based models that we typically apply on shorter time scales and smaller spatial scales, to much more efficient but simpler, much less complex, and behavioral kind of based models. In this study, we're interested in predicting changes in medium to long time scales, and so we're looking at families more of behavior kind of models than process-based models. So when we're looking at these kind of time scales, some of the most important processes that we're looking at, or we'd like to be able to take into account, are the impacts of climate change. For example, sea level rise, as shown in the top right from the SROCC. We see in the inset the predicted sea level rise for two of the extreme scenarios that estimate global sea level changes on the order of 32 centimeters to about a meter by 2100. And in the bottom right, we have changes in the wave climate, where the plot is showing a percent change in the mean significant wave height in different ocean basins, where that can range from plus or minus 10% change from the currently observed values. So we'd like to try to take into account these changes in sea level and changes in the wave climate. There are a variety of different approaches that exist, ranging from simple approach of linear extrapolation, where we're resolving or thinking that we're taking into account both waves and sea level rise. We assume, though, that we can calculate a constant trend using historical data, and then we can extrapolate that into the future. It's limited by the fact that we need observations, a significant amount of observations in the past to calculate these kind of trends, and this is very sensitive to the time period that's used. For looking at the impacts of sea level rise, the most commonly used approach is the Brun rule that assumes a very simple equilibrium profile that will be translated both horizontally and vertically with changes in sea level. This is very highly sensitive to the parameters that are used in this, and its applicability has been questioned in time. A more recent approach developed by Bano and Kuriyama in 2014 was using a probabilistic modeling approach, where they're taking into account only waves, although this can be coupled as they did with something like the use of the Brun rule, where you generate realistic wave time series in the future by adjusting the wave height distribution using projections from global wave models. And then you have to choose a selected morphological change model to be able to predict those changes in time. And finally, another recently proposed approach, the probabilistic coastal recession model of Ranasingh et al., takes into account both sea level rise changes and the impacts of storms by using a selected erosion model to model erosion during storms, and just assuming linear accretion between storms. Now, the generation of this storm time series is quite complex, so it's limited by the mathematical complexity to develop this kind of approach, and the fact that we're assuming linear beach recovery in between storm events. So if we move on to looking at our particular study site, we're working on the beach. It's called Vougot. That's on the northwest coast of France and Brittany. It's located here. It's a 2-kilometer long beach. It's backed by dunes. It's a macrotidal beach that has over a 7-meter tide range, where both cross-shore and longshore processes can be important, as you can even see by the observed offshore variability in the bathymetry. So we have monthly DGPS surveys since 2004 in the first 3 profiles, and since 2011 in the second set of profiles, and hourly wave characteristics from the WaveWatch 3 model outputs from the now, and hourly tide level predictions from the SHAM at a nearby site. So now we're using an equilibrium modeling approach, and we apply this equilibrium model at elevation contours from -1 to +6 meters along the intertidal profile. And if we look at the results of that, on the right here, we're showing the R-squared value, the correlation between the observed and simulated contour elevation changes in time. We see very good agreement between the model and observations in the lower intertidal beach profile, as well as in the upper intertidal beach profile, with a decrease in the R-squared value between about 2 and 5 meters. And this is a zone where we typically call kind of the pivot point, or the transition zone, where we see that sediment passes from between the upper and lower intertidal beach, and the dynamics in this kind of mid-range are a bit more complicated to predict. On the left side, we have 3 different examples. So from the contour elevations that are indicated on the right, the mean water level, the mean high water neap, and the mean high water spring. And we see overall a rather good agreement between the model in blue and the observations in green at these 3 locations, except perhaps at the highest one here at the mean high water spring. We don't capture exactly the variability in the beginning of the time series when able to predict this large accretion event at the end of the time series. So how can we predict future changes? Well, thinking back on those 4 different approaches that were proposed in the literature, I'll first start by looking at applying the linear extrapolation method, where we calculate historical linear trends. For example, on the left, of the mean high water neap, the blue points are representing our observations, and the red line is the linear trend. And then we can extrapolate that into the future. So we've done that. And the right panel here, we're showing the extrapolated contour position change for the 3 contours we identified previously, the mean high water neap, mean high water spring. And we see changes in the predicted on the order of 70 to up to 120 meters of contour position change at these 3 different elevations. So we see the sensitivity to what elevation you choose, as well as to what time period may be used to calculate these kind of linear trends. And finally, we notice here that we see crossing of some of these lines, which gives us quite non-physical results. If we want to look at taking into account the impacts of sea level rise, the Brun rule is the most commonly applied approach. And this is where we calculate the coastal recession, or R, as a function of the surf zone width L, the sea level rise rate S, the berm height V, and the closure depth H. So if we estimate the sea level rise, we have 2 different estimates here, one in blue being the mean IPCC projection, that is a global value, and the orange line here being an extrapolation of observed sea levels at a nearby port of Brest. we see the difference can be quite significant. The other model estimated values of the model parameters are shown here for the berm height, closure depth, and surf zone width. And in doing this kind of a test, we decided to do a sensitivity analysis of running a large number of simulations and calculating the Sybil indices to see which parameter the model was most sensitive to which parameter. And for this beach profile that we're looking at, it was the sea level rise rates that were the most determinant. On the right now, we're looking at the estimated shoreline retreat, which we see reproduces very well or very similarly the curves of the sea level rise on the left. We end up predicting on the order of 15 meters of retreat if we're using the observations of sea level changes, or the extrapolated trend from observations, versus using the IPCC predictions in blue, where we have somewhere in the order of 35 to 65 meters of shoreline retreat. So finally, if we look at the probabilistic modeling approach, we look at predictions that can be made at the mean sea level, where we have in blue, orange, and green curves are the mean of 200 different Monte Carlo simulations of future wave predictions for A1, B, A2, and B1 projections of climate scenarios. And if we focus into the first 10 and last 10 years of those time series, we see the red zone here is the data that was used to calibrate the model, and then we make these forward predictions in time, where we see from one scenario to another, we can have on the order of 10 to 15 or so meters of variability. And the three wave projections differ only very slightly because the statistics and wave height distributions are very similar between those three projections. And so we see by the end of our time series, the equilibrium model predicts a very similar kind of constant say changes on average between the 200 different simulations, where we see no significant long-term trends. So we see in summary very high variability between different approaches in trying to predict medium to long-term beach evolution. And this is very highly dependent on the processes that are considered, so whether it's sea level rise only, wave climate changes, or both. And it's also very sensitive to the kind of modeling approach that we may use, for example, in choosing a probabilistic kind of modeling approach. So what now? Our recommendation really is looking at trying to rethink past models and assumptions to go beyond existing approaches to develop new ones, as we're currently working on our lab. Thank you very much for your time.